Okay, welcome everyone. We're just about to get started. I just want to give everyone a chance to join the class. So my name is Ali. I'm going to be going through just a few things or a few topics that we will look at relating to the summer examination. So I've shared the screen. Hopefully all of you can hear me quite well. What I'm going to do now is I'm just going to pull up my notes. And what I just would like you to do is I'm going to have the screen in front of me. So hopefully you can all see this. If there's any issues, all I want you to do is unmute yourself and say, listen, Ali, I can't really see that or I can't hear that. Or if there's any questions that you want to pose at me, you absolutely can. I will always give time at the end as well to if anyone wants to ask a few extra extensive questions. So for now, you just let me know if anyone is having any issues with seeing the screen.
Hey Ali, we're all good. Just to let you know the students' mics are muted, so it'll be coming through the chat.
Perfect. Okay, thanks a million for that, David.
Cheers.
Okay, so what I'll do is because all of your mics are muted, if there's any questions, you can put your hand up and I'll just go back and forth. But I will try and get all your questions done at the end because, you know, we do have an hour and 15 minutes, so we have quite a bit to cover in that time. So we're going to get started now. So we're trying to give you a bit of a kind of idea of what you can go over during the summer examinations. Now, depending on the fact that the majority of you are all going from different schools, your teachers may have covered a few of the different topics. So what I tried to do is I've compacted down certain topics that I know that your teachers would have covered in fifth year. So the first one we're going to have a look at is the atomic structure. Okay, so we're just going to go through briefly what you really need to know in relation to it, the history of the atom, the subatomic particles, and so on. We will then move on to the electron arrangement. We'll have a look at chemical bonding, and we'll have a look at the mole concept and stoichiometry. Any of the ones that we don't get covered, I will give you a little bit of a brief. You can get the notes on Monday if you want to request them, and I'll give you a bit of a brief of what else you probably can cover. So the first one we'll have a look at is the atom. So we can see, and we should know from junior cycle, as you can see on the screen we have here, there are three subatomic particles that are part of the atom. So the first one we have is the proton, the neutron, and the electron. Now, what you need to know at leave insert is you need to know their charge, whether they're positive, neutral, or negative, and you need to know the relative mass of our proton, neutrons, and electrons. So what we know is P for positive, protons are going to be a positive. Neutrons, it's in the name. Neutrons is neutral. So our neutrons is going to be zero or a neutral charge. And lastly, our electrons are negative, okay? Now, in relation to the relative mass, we would say, when we say relative mass, we're not saying that the mass is one. We're not using a unit for, we're not saying it's 1 gram or 1 milligram. We're trying to give people an idea that the proton and neutron have a relative mass of 1, meaning that the proton and neutron are relatively the same mass. The electron is actually 1 in 1,835, which is quite a lot smaller than, let's say, your proton and your neutron. So it's just trying to give you the scale of the size of what a proton, a neutron, and electron are. Now, in terms of the orientation around the atom, we know the protons and the neutrons are located in the nucleus, and the electrons are located orbiting our nucleus around the atom. Now, it's really important when it comes to the atomic structure that you know the history of the atoms and the scientists that contribute to them. So I've given you a little bit of a breakdown of the scientists that had a part to play in the development of the atom. So the first one is Democritus. He's an ancient Greek philosopher, and he was the first one that suggested that matter cannot be cut into smaller pieces, or if you want to be a little bit more specific, that means indivisible. We then have Dalton. Dalton then actually just extended on Democritus' work, and he proposed the first atomic theory suggesting that atoms are indivisible particles, very much like Democritus, but this time he actually was able to contribute and say that they combine in fixed ratios to form compounds. So he was actually able to come up with the idea of not only are we dealing with atoms of elements, but we now can actually see certain atoms of elements can actually create a molecule or a compound. The next one is Crookes. He's not one that comes up all that often, but he is one that investigated the properties of cathode rays using vacuum tubes, laying the groundwork for the discovery of the electron. You then had Stoney, again, not really someone that usually comes up. He was the one that named the electron as a fundamental unit of an electric charge. Now, this is where you can see I've in red. Thomson, he's huge. He comes up all the time. Himself and Rutherford are the two scientists that probably paved the way for the actual discovery of the development of the atom. So you do get asked questions an enormous amount about Thomson and Rutherford. So Thomson discovered that by the use of cathode rays, when they were composed of negatively charged particles, which he was able to identify as electrons. So he was able to see that there was negatively charged electrons that were being bombarded, and around the cathode rays, he noticed if they were negatively charged, they must obviously have some sort of fundamental part to play in the atom. So when he noticed that they were negatively charged, he then was deciding to call them electrons. He also was able to measure the charge of the mass ratio, i.e. your E to M, the electrical charge to the mass of the electron. Now, this part is important. I have seen this come up before. So just to make sure that if you ever get asked a question where they're asking about the ratio of mass to the charge of an electron, that you do look at Thomson. Okay. Now, the next thing that's really important about Thomson is this diagram here, known as Thomson's plum pudding. Now, the name they obviously came up with, I always think is kind of humorous because I don't think it looks like a pudding, but they came up with the idea, given the fact that they're using dots and crosses the whole way around it, they said it looks something like a Christmas pudding because the dots and crosses are embedded in the blob of sphere. It's looking like that it's just like the raisins or the fruit that would be around the pudding. Now, you do get asked to draw this quite a lot, and it's relatively straightforward. When it comes to Thomson's plum pudding, what they know at this stage is they're electrons. So we can see the electrons are negatively charged. We also know that there is a positive charge. So if you see, it says a sphere of positive charge with electrons embedded in it. But at this point, they didn't know the orientation of the positive protons or the negative electrons. All they knew that within the atom, there was positive and negative charges. So this was a pretty big contribution, but it still was not giving us the correct orientation of the atom. So make sure that you do know Thomson's plum pudding for the summer exams, definitely, and obviously for the Leaving Cert as well. It does appear quite a lot. So when you are drawing it, make sure that you don't have any orientation of your negatives and your positives, and then make sure that you do say that the electrons are embedded in a sphere, or you can use a blob of positive charge. The next one we're going to have a look at now is Millikan. Millikan, again, small amount. He did obviously make a contribution, but he doesn't come up all that often. So Millikan was the one that measured the magnitude of the charge on the electron through the oil drop experiment. Now, you do need to know that the experiment that he did to kind of contribute to the electron was the oil drop experiment. And then lastly, we're down to our other big scientist, which is the Rutherford. So Rutherford, he used a gold foil experiment. Okay, and this conduction of this gold foil experiment was actually probably the most revolutionary in terms of how we actually look at our modern atomic theory now. So he really, really paved the way where we now look at the orientation around the electron. Now, when it comes to the gold foil experiment, there's two things that you need to know. You need to know the steps of what his predictions were, what he was expecting to happen, because we remember when Rutherford was doing this experiment, his modern or current atomic theory or atomic model was Thomson's. So that's what he was assuming that the atom looked like. Now, so he made predictions. Now, when he did the experiment, he noticed that his predictions were not true. So he actually came out with realizations or conclusions. You need to know both, okay? On top of that, very rare, but I do see sometimes that they'll ask you to draw the model of Rutherford as well. So we're going to just go through the step by step. If you look at the model, first of all, what you will notice is that we have the positive charge in a very, very concentrated, small, dense nucleus. Okay, that's in the center of our atom. The next thing you will notice is instead of it being positive and negatives the whole way around, you will notice that the negatives are around the nucleus, but they're quite far from the nucleus. We still at this stage don't know the orientation of the electrons, but what we do know is that they're not all over the atom. Okay, you'll see that there's actually quite a bit of space between the nucleus and the electrons. And this was the fundamental conclusion that Rutherford was able to draw. So just make sure that you are able to draw the Rutherford model. The next part is make sure that you know these points. Okay, these are the only points that you necessarily need to know in terms of the gold foil experiment. So 1, most of the particles, and you need to remember that the particles that are used in the gold foil experiment are alpha particles, which are positively charged. For those of you that have done radioactivity will know this about alpha particles. Some of you may not have done radioactivity yet. So the particles that are used in the gold foil experiment are alpha particles, which are positively charged. Now, what he was expecting that when they went through, they would be deflected at very large angles. But what he actually noticed is the majority of the particles actually went straight through. So they didn't hit off anything, they didn't come near any charges. So he was like, okay, that's not the prediction I had. I predicted that they were actually going to be deflected at very large angles because they come close to a positive charge or negative charge or positive charge. But what he noticed was they actually just went straight through. So he was able to conclude from that, and this is your conclusion here, that the atom must be made up of mostly empty space. The next thing was some of the alpha particles actually bounced back along the original pathway. So why did some of them actually directly come back instead of being deflected? So some of them bounced back because they must have hit something that was so strong and concentrated in positive charge that the repulsion was so strong that the positive alpha particles came directly back along the original pathway. So for Rutherford, he came up with the conclusion that they obviously hit a very small, very concentrated, very dense positive nucleus. So there again, he noticed that the positive charge must be altogether in a concentrated space. And lastly, a very, very small amount, and usually people only learn the first two, but you do need to know the third part as well. A very, very small amount of the actual alpha particles were actually deflected at a large angle, now very large angle. So what conclusion did he come up with this? Well, he was like, okay, if they're not going straight through, they must be coming close to something because they're going through and then they're going deflection at a large angle, which means they must be coming close to something that's repulsing them. And if they're positively charged, what they must be coming close to is another positive charge. Therefore, they're coming close to the nucleus. So the three things that he actually noticed and the three conclusions came up was, one, most of the particles went straight through. So the atom is made up of mostly empty space. Two, some of them actually bounced right back along the original pathway, so they must have hit a very small, concentrated, dense nucleus. And three, some were deflected at very large angles, so they must have come close to the nucleus and been repulsed or repelled by the positive charge of the nucleus. Now, they're really, really important because you do get asked quite a lot about Thomson's and Rutherford, and it never deviates away from Rutherford talking about his predictions and his conclusions. Now, the next one we have a look at is Bohr. Bohr was also fundamental in proposing the structure around our electrons arrangement. He was the one that actually was talking about the electrons being orbiting the nucleus. So he proposed a model where the electrons move in fixed orbits around the nucleus and with specific energy levels. And the last one is Chadwick, who discovered the neutron, completing the model of the atom. So as you can see, the likes of Chadwick, Millikan, and so on, the smaller ones, they do come up, but they don't come up as much as Rutherford and Thomson. So I would really focus on them. Now, the next thing we'll have a look at relating to atomic structure is isotopes and atomic mass. Now, isotopes are atoms of the same element with the same atomic number, but different masses number due to varying number of neutrons. So what we know is our subatomic particles are protons, neutrons, and electrons. Our protons and neutrons are making up our nucleus, and that is your mass number. Your atomic number actually gives you the number of protons, and it also gives you the number of electrons, because you'll always have the same amount of protons and electrons. So an example we have is carbon-12 and carbon-14. They are both isotopes of carbon, but they differ because they have different mass numbers based on the number of neutrons. The next one we have a look at is relative atomic mass. You do get asked this definition, so you should know it. It is defined as the weighted average of a mass numbers of all naturally occurring isotopes of an element based on the carbon-12 scale. Now, an example would be the relative atomic mass of chlorine is approximately 35.5 due to the presence of isotopes of 35 chlorine and 37 chlorine in different natural abundances. Very rarely, you do get asked to actually calculate the relative atomic mass. So I've given you an example here on how you calculate the relative atomic mass. So if you're given a percentage of, let's say, an isotope, here we have 79% of magnesium-24. And we have 10% of magnesium-25 and 11% of magnesium-26. Now, that tells us that's the amount or the percentage of magnesium we have of those isotopes, mass number of 24, 25, 26. So what we do to find the relative atomic mass is I take each of the mass numbers and I multiply them by the percentage of what we have of them. So it'll be 79% by 24, 10% by 25, 11% by 26. I will add the sum of them up and I would divide them by 1,000 to negate the percentage. And what we'll come out with is 24.32. Now, that's a relative atomic mass of our magnesium. If you go to the periodic table, you will see that our MR, or mass number of magnesium, is 24.32. So again, what I'm saying with this one, this is a rarity. It doesn't come up all that often in the Leaving Cert, but I have seen it posed. So you should be familiar with how to do the calculation. And your examiner or your teacher may ask this question in the summer exam. Okay, now I'm just going to swiftly see if there's any, no hands up. So we're going to continue on. Now, the next thing is mass spectrometry. So again, we're still talking about the atomic structure. We're still relating it to the mass. If you think of this, mass spectrometry is a spectrum that we can use, or a spectrometer that we can use, that measures the mass of our elements, i.e. the amount of protons and neutrons that you have. So we're still looking at our atomic structure and our subatomic particles. So the mass spec is a technique that is used to determine the relative atomic mass of elements by measuring the mass of their ions. This process involves several key stages. Now, you have 1, vaporization, 2, ionization, 3, acceleration, 4, separation, and 5, detection. In a Leave Insert exam, what you're asked is not how to define them. What you're asked is, usually you're given 2 out of the 5 of them. And then they ask you to give the other 3 and then list them all in order. So what you need to know is, you need to know vaporization, ionization, acceleration, separation, and detection. But not only do you need to know them, you need to know them in the correct order. You don't actually necessarily have to give the definitions for them. You just need to essentially know their headings. So the first one is vaporization. Now, it's in the word. Vaporization is a process where we convert a liquid to a vapor, a gas. So the sample is a liquid and it's vaporized into a gas. The second step is ionization. Again, it's in the word. Ionization is a process in which we produce ions, convert our atoms to ions. So how do we convert atoms to ions? We need to gain or lose electrons. More specifically, though, in the mass spec, the atoms will be converted to positive ions, so they must lose electrons. The third one is acceleration, which means these ions are accelerated in an electric field. The fourth one is separation. Now, if you think about it, if we have different mass numbers, and let's say we've got a mass number of 24 or a mass number of 22, we will know the mass numbers are obviously going to have a certain way of how much they can be accelerated. So because of this, they're easy enough to separate it. So if we accelerate both of them, one will move at a higher acceleration, the other will move at a slower acceleration. So this is how we separate the ions out based on their mass to charge ratio in a magnetic field. And lastly, the detection. Ions are detected and their abundances are measured, and then it comes out on a computerized graph paper that we can then have a look at. So this is important. I'd be very surprised if you don't get asked these in your exam. I know I would definitely be asking these in an exam. So the mass spec, just make sure you know all 5 stages and you know them in the correct order. And like I said, you really only ever get asked the headings, not necessarily how to actually explain or define them. Okay, now that is relating to the atomic structure. So all I'm saying is, when you're talking about the atom, know your charges on your subatomic particles, know your orientation of them, know, and this is the most important part, know the history of the atom. Okay, know about your scientists that paid a huge contribution, specifically Thomson and Rutherford. Now, we're still with the atom, but we're moving a little bit more into subatomic particles. We're going to look at the electron. So we talk about Bohr's theory because, remember, at this point we know about our electron, we know our atomic structure, we know the electrons are further away from the nucleus, but we don't necessarily know their orientation. Enter Niels Bohr. So Niels Bohr came up with a theory, and his theory was that electrons occupied specific energy levels around the nucleus. Okay, so he was saying, okay, I think that they're actually occupying and they're orbiting around the nucleus, but they're in specific energy levels, which means that they're at levels of energy. Depending on where they're located, they have a specific amount of energy. That's what it means by the energy levels. So this was his theory. He actually carried out a mathematical equation to use this theory, to test his theory. But he then actually carried out an experiment to see if his theory was correct. So he used an instrument known as the emission line spectrometry, or we call it the emission line spectrum. Now, when he used the emission line spectrum, he only did this for hydrogen. He didn't do for any of the other elements. He was only looking at hydrogen. So what happens when it's put into the, you're using the emission line spectrum for your instrumentation? So these are the steps, and I can't be emphatic enough that learn these steps off. Because regardless of the question, if you ever get a question in the Leave Insert or in your summer exam where they're talking about the emission line spectrum, and they're talking about how did this affect the atomic theory, or how did this affect the atom, they want to know what happened to the electrons within the atom. So the first one is, the electrons in the ground are always starting in ground state. They absorb the energy. Now, we know anything that absorbs energy is going to become excited. So when they absorb energy, they become excited. If they become excited, they're going to move, i.e., they're going to move to a different energy level, a higher energy level. This is called the excited state. When electrons fall back down to the lower energy levels, they emit energies in the form of a light, also known as a photon. So you can say form of a light, you can say photon, either is acceptable. Now, just one thing to note, emit means give out, okay? Just in case, so you can say give out or release, just in case anyone isn't sure of the word emit. So emission line spectrum is a spectrum that actually shows lines on a dark background, and the lines that it's showing is actually light energy, okay, that has been given out. That's why it's called emission line, because it's giving out the light energy. When the light energy is given out, it's all to do with the electrons falling back down to lower energy levels. So this is where it's most specific. It's when they fall down to the lower energy levels, they emit energy in the form of a light. Now, another question that can be posed is, why do they not stay in the higher energy levels? The reason they don't stay in the higher energy levels is because higher energy levels are unstable. So they're not long lasting. Now, when they fall back down and they emit the energy in the form of a light, the electrons will release a light that is has very specific frequencies when falling between energy levels. And this produces a line spectrum where these lines are on different frequency. Now, when Bohr did this actually proved his theory. It supported the idea that there are energy levels, because if an electron was falling from energy level 5, which is a really high energy level, really far from the nucleus, and if it fell to energy level 4, it would emit a certain amount of energy. If it fell from 5 to 3, it would emit another certain amount of energy. So the energy that they've been emitting, depending on which energy level they fall, is all different. So that was actually proving his theory that because we could see different frequencies of light, they must be falling from at different energy levels and emitting different amount of energies. So when it comes to Bohr's theory and relating to the emission line spectrum, he used this instrumentation to prove his theory. And you need to know the step-by-step of what actually is occurring in the atom. Those steps are what you need to know. Okay. Now, there is another instrument that supports the energy levels, and it's known as atomic absorption spectrometry, AAS. You do need to know this one as well. This one, Bohr didn't use to prove his theory. He only used emission line spectrum, but the atomic absorption spectrometry is another instrument that also supports the idea of energy levels. So this time, if you read it, it says atomic absorption. So the other one was emission, giving out light energy. Atomic absorption means it's taking in energy. So it's essentially same kind of spectrometry. The only difference is it's looking at a different part of it. Instead of giving out the energy, it's taking in the energy. So what it does is it measures the concentration of elements by detecting the light they absorb of specific wavelengths. Now, I've given you a little diagram of what they actually look like. You don't need this diagram. It's just to show you what emission line spectrum and atomic absorption spectrum look like. And you see they're very similar. So both instruments are very good in the use of chemical industry because they're used for detecting unknown substances. So they can be used in forensics, they can be used in medicines or medical companies. They can be used for quite a lot of different things, but they are fundamental for us to identify unknown metals or unknown substances. So as you can see, I've given you an example of an atomic absorption and an emission line spectrum specifically for hydrogen. Now, let's look at the emission line spectrum first, because that is the one that you're dealing with. The emission line spectrum is on a dark background. The atomic absorption spectrum is on a colored background. The emission line spectrum it gives out light energy, and the light energy it gives out is measured there at different frequencies. Now, the atomic absorption is on a colored background, and see the dip in light. That is where the electrons are absorbing that light energy, hence why there's a dip. What you will notice about the two of them is the hydrogen ones, the frequencies are identical. So every single element has its own specific frequency, very much like a fingerprint. So as you can see there, depending on which instrument you use, you're still going to get the same frequency. And like I said, you don't need to know this. This is just to give you an idea of what it would look like using the spectrums. So AAS is used in water and blood analysis. ALS is used in astrophysics, identifying metals. And you should have done this experiment, flame test, also one that you should know. The flame test is it's a very foundational way of actually doing your emission line spectrum. So I'll give you a little short one there. Emission line spectrum releases energy in the form of light. Atomic absorption spectrometry absorbs energy in the form of light. Now, another thing, and you only need to know a very brief one about this, is known as the Balmer series. Now, this series is part of the hydrogen emission spectrum, where the electrons fall to n is equal to 2 energy level of the hydrogen atom. So actually, instead of them falling to n is equal to 1, because that's the closest one to nucleus, they only fall to n is equal to 2. When they fall to the n is equal to 2, this is the only time you can actually see a visible light. They may fall to other energy levels, but it's only when they fall to n is equal to 2 level that they see the emission of a visible light, bright lights at a specific wavelength. So this provides evidence also for quantized energy levels. You can get asked about Balmer series, but the only thing they will ask is, in which energy level will the electrons fall to see the visible light? And you will always just say n is equal to 2, energy level 2. Okay, either of those is absolutely fine. So we're not saying that in the Balmer series that if the electrons don't fall between other energy levels. We're just saying when it falls to the n is equal to 2 energy level from a higher energy level to n is equal to 2, this is where we actually see the visible light, where we see the specific bright lights on the wavelengths. Now, the limitations to Bohr's theory, as you can see there, I've given you 4. You need to know them. You usually get asked 3, but it's always good to have an extra one in the bag. So, limitations. 1 is Bohr, he came up with foundational fundamental theories around the electron arrangement, but he only worked with hydrogen. So he did not account for any other atoms that had more than 1 electron. The second one is he did not consider electron wave motion. I'm going to go through that in a minute. The third one is Heisenberg's uncertainty principle. Know this definition. You are likely to get asked this definition in a summer exam. Heisenberg's uncertainty principle, we know, is it's impossible to find the exact location and the velocity of our electrons simultaneously or at the same time. And lastly, even though Bohr had considered energy levels, he hadn't considered orbitals or sublevels within, i.e., the subcategories of our energy levels. So make sure that you do know the limitations of Bohr's theory, because you will always get asked them as well. So Heisenberg's uncertainty theory, or uncertainty principle, this principle was actually the one that kind of put limitations on Bohr's theory, because Heisenberg had come up with the theory around, or the principle around, that it is not possible to measure the exact location and the exact speed of the electron at the same time. Why? 1, electrons are very, very small, and 2, electrons are constantly moving. So because of this actually disproved part of the theory that, let's say, Bohr had, where he was saying that the electrons were in fixed orbits. We know now that they're not in fixed orbits. So what we actually know, that there is not a certainty that we can actually locate an electron, but we can only ever look at finding an electron with high probability. So it's all about probability, the high probability of where we may find the electrons, not a certainty. So that was a huge disprovement in Bohr's theory. Now, as you can see, I've written this NB, wave nature of electron. This is really important. If you ever get asked a question, sometimes I find the students get very confused in ways some questions are posed. So let's say they're asking you a question about the modern atomic theory. Okay, a lot of people go into modern atomic theory that they're small, and the orientation, they talk about Bohr's theory. If they mention for you to talk about the modern atomic theory, but they ask you about electrons exhibiting or giving out or acting, what way that the electrons may exhibit, they will always mean talk about the actual behaviors or the characteristics of the electron. Okay, the exhibit is kind of the key word there. So if they ask you about electrons in the modern atomic theory, and they're asking you to talk about what they exhibit or what properties they exhibit, you want to be talking about wave-particle duality. So what is wave-particle duality? So wave-particle duality means that an electron will have the properties of both particles and waves. Now, what does that mean? Particles, what we know about a particle, we've got our electrons, we've got our protons, we have neutrons. They have a mass and they also have a charge. Okay, so that's how we would call them. That's because those 2 properties, that's why we would say they're a particle. Now, the difference with a wave is, a wave, and we should know, you may know this as well from physics, a wave can actually carry energy from one area to another or in one form to another. But the difference is that they don't necessarily have a mass. So this is where the electrons were, some people are getting confused on the electrons, or scientists are getting confused on the electrons, because it's a particle that has a mass. But remember, if you look at the size of the mass of electrons, it's nearly negligible. It's so small that actually means the electron, because the mass is close to negligible, it means that the electrons being that small actually can have particle properties because it does have a charge, but it also can have wave properties because the mass is so small that it's nearly negligible. So just make sure that you know that electrons can exhibit both wave and particle duality. Okay, the next thing we will look at is atomic orbitals. So an atomic orbital is a region, and this is a definition. If you see any red italics or definitions, you need to be learning. So an atomic orbital is a region of space. Make sure you say region. You don't say area. Area is not correct. You'll lose marks if you say area. You can say a region of space where it is most likely to find an electron. Okay, so this is where we're talking about our orbitals. Because we now know, due to Heisenberg's uncertainty principle, that we don't actually can say with certainty where the electron can be located. We can only say that with high probability where we're going to find an electron. So an atomic orbital is the space where we're most likely to find the electron. Now, for leave insert, you need to know, we know that there's 4 orbitals we look at, S, P, D, and F, but that's only when we're doing our electron configuration. When you're talking about being able to, visualize or draw the shapes, you need to know the shape of the S and you need to know the shape of the P. Now, the S will always be a spherical shape, so you just draw a circle, okay? Your P, because we are thinking about 3-dimensional, you need to draw them like dumbbells or like figure eights. So you would draw it like that. That is, as we can see, that's on your y-axis. You draw it like this, that's on your x-axis, and then you draw it like this is on your z-axis. And that is essentially just covering the fact that it's a 3-dimensional shape. So be very careful that you do know those shapes, because again, I'll be very surprised if you don't get asked about the shapes. Okay, just checking to see any hands up. Now, when we talk about orbitals, they're the shapes. We've got S, P, D, and F. Let's talk about our configuration. Okay, so in S, P, D, and F, we have our S orbital, and we're talking about any of our orbitals. Our orbitals can only ever hold a maximum of 2 electrons. Now, we may have more than one orbital, like we can have 3p orbitals, we can have 5d or 5d orbitals, we can have our 7f orbitals. So you can have more than one, but one specific orbital can only ever hold a maximum of 2 electrons. Now, this is known as the Pauli exclusion principle, where no more than 2 electrons can occupy a single orbital. And when they do, they must have an opposite spin. So if we were to draw, let's say I'll just draw the s orbital. So let's say we have an s orbital, and I'm just drawing the box there to represent an s orbital. I'll do 1s, okay? Now, that's an s orbital in the first energy level. And what we mean is we can only ever have 2 electrons within that orbital. Now, what you'll notice is we draw them in opposite spins. And the reason why we draw our electrons in opposite spins is because they're both negatively charged, they're in close proximity to each other, they're repelling each other. They don't like charges do not like each other. So they're repelling each other. So by going in opposite spins, what they're trying to do is reduce the amount of repulsion by going in opposite spins or opposite directions. So when you're drawing it, just make sure that you're showing 2 half arrows going in opposite direction to show the opposite spins. Now, the Aufbau principle states that the electrons will always occupy the lowest energy level available when the electron is in ground state. The reason why they always occupy the lowest energy level is also because it's closest to the nucleus. The electrons are attracted to the positive of the nucleus, hence, so they want to be closest to the nucleus. The closer you are to the nucleus, the lower the energy of our actual energy levels. Now, the s orbital, like we said, is spherical in shape, but there's only ever one s orbital in every energy level. So in the first energy level, there's one s. In the second energy level, there's another s orbital, but we would say it's 2s because it's the second energy level. In the third energy level, there's only one s orbital, in the fourth, and so on. So what we can see there's only ever going to be one s orbital in each energy level. Therefore, in the s orbitals, you'll only ever have a maximum of 2 electrons. Now, the p orbital, we know, has a dumbbell shape. There will always be 3 p orbitals in each sublevel. The reason why there's 3 p orbitals is because we're looking at the x, y, and z axis. So we need to have 3. Now, we will go into energy levels to see where we can see. So we know we've got our s, and we have our p, and we have our d, and we have our f. And that's our orientation. You always start with an s, then you go to a p, then you go to a d, then you go to an F, okay, in each energy level, okay? S, or we look at our first energy level, we only have S. If we look at our second energy level, we have S and P. If we look at our third energy level, we have S, P, and D. If we look at our fourth energy level, we have S, P, D, and F. So the actual number of the energy levels will tell you exactly which type of orbitals will be in it. So in the first one, it's only going to be S. In the second energy level, S and P. third energy level sp and d, and fourth energy level sp, d, and f. So the p orbitals are the right angles to each other, shown on the diagram. It is important to note that any p sublevel will occupy 6 electrons. And that means because if one p orbital can have 2 electrons and we have 3 p orbitals, then they're going to occupy 6. Like I said, we then have d orbitals. There's going to be 5 of them. Okay, whichever energy level our d orbitals start in, there'll be 5 of them. It's not required that you know the names or the shapes of these orbitals, but it is important to know that d sublevel will be able to accommodate 10 electrons because 2 will go into one of the 5, 2 will go into the second of the 5, 2 will go into the third of 5, and so on until we have 10 electrons. So if we have a look here, the first 36 elements on the periodic table have the main energy levels 1, 2, and 3, which is further subdivided into our orbitals or sublevels sp, d, and f. So the first energy level contains 1s with a maximum of 2 electrons. The second energy level contains 2s and 2p, and we know that an s can only hold 2, a p, because we'll always have 3 of them, will hold 6. Then in the third energy level, we'll have an s, we'll have a p, and we'll have a d. But s can only hold 2 because there's only one s. P will have 6 because we have 3 of them. And because a d orbital or the d orbitals, we have 5 of them, each of the 5 can hold 2. So there's going to be 10. So in total there, we would see we have 10, 6, and 2, which is 18. Here we would have 8, and here we only have S2, which is 2. And then the last one, we then have our 4s. Now, the fourth energy level contains 4s, and the 4p will start to be filling up, then the 4d, and so on. So we go down to our electron configuration. As you can see, I'm going to do iron with you. Just let me get an iron we look at. I'm just going to get periodic. We go to the periodic table, which we have here on my screen. Makes it a bit easier. Maybe we'll go with okay, we'll go with calcium actually, because it's just a little bit quicker. So I'll just change that to calcium. So what we're going to do is we're going to go through our electron, how to write your electron arrangement. As you can see, hydrogen only has 1 electron. It will always occupy the first energy level first, which is 1. And we only have an s orbital in the first energy level, so that's going to occupy that. We can only hold a maximum of 2, but there is only 1, so it's 1s1. We then go to oxygen. Oxygen in group 6, so it has 6 electrons in its outer shell. So the first energy level will only have an s orbital, so 2 electrons out of 6 will go into the s orbital. We then go into the second energy level, and we have an s and a p, so 2 out of the 6 will go into the s orbital, 4 then, the remaining 4 will go into the p. And then lastly, we have fluorine, which we have 1s, 2s2, and 2p5, which represents that we have 5, 6, 7, 8, 9 electrons in total. Now, our calcium has 20 electrons. So let's go through this because I want to make sure that you're writing your electron configuration correct. So we always start with the first energy level, 1s. And we know it can hold a maximum of 2 electrons, so that's 1s2. We then go to second energy level that can hold 2s and 2p. So it'll be 2s and it holds a maximum of 2. So I put 2 in there, and 2p will hold a maximum of 6. So that's 6 there. Now, at this point, what I do is I add them up. 6, 7, 8, 9, 10. So what I've done is I've accounted for 10 out of the 20. So let's go on. So we've got 2p. We then go into our third energy level. I'm going to have 3s, 3p, and 3d. Now, we'll occupy our s. That's going to give me 2. We then have p, which will give us 6. So now let's add that up. I've got 10, I've got 16, and I have 18. Now, I have 2 left. So a lot of people would then write 3d2. Okay, because you've got 10, 11, 12, 13, 14, 15, 16, 17, 18, and the remaining 2 out of the 20 goes into 3D. But if you actually remember from your off-bow principle, your Hund's rule and Pauli's exclusion, is that the 4s orbital actually has slightly lower energy than the 3D. So it will actually be occupied first. So instead of putting the 2 electrons into the d orbital, we put the 2 electrons into the 4s orbital, okay? And if you're going to 5s, that would also come before the 4d. So this is a really important one. Now, if you had more than 20, let's say we're 21, then you go 3d1, okay? You then will fill the 3d orbital. But remember, you always fill the 4s orbital before the 3d when you're doing the electron configuration for any element that will go up into the 4th energy level. Okay. Now, what we're going to do is we're going to move on to the mole and stoichiometry, because I know you should definitely have got on to calculations at this stage of 5th year. So what I want to do is actually go through some of the maths calculations with you, because I know sometimes they can be a little bit tricky. So I'm giving you a quick brief one through the mole concept, because the mole concept, you've got a few definitions you need to know. The base thing that you really need to know about the mole is a unit of measurement. Like we use centimeters cubed or meters cubed or liters, it's a unit of measurement. And as you can see there, as I put, the mole is a unit of measurement, and it just tells us the amount we have of a substance. Okay. Now, more specifically, what we can do is actually work out not just the amount we have, but specifically the amount of particles we have. And how we do that is we will always take the mole and we multiply it by Avogadro's constants, 6 by 10 to the power 23. Now, you're given that in the leaving cert, so you'll be given that in the exam. So you always just need to, you don't need to learn it off, but I'm sure, to be honest, if you've done calculations, you definitely have familiarity with this. So the next part we want to do is, before we go into our calculations, I'm going to give you this triangle, which I'm sure you're familiar with. Okay, this triangle, I call it the trusty old triangle. This is a lifesaver when you're doing any calculations. Even the further you go into your concentrations, you're going into your balanced equations, stoichiometry, this is a lifesaver. Your mass is always in grams. Your moles is represented as N, and your MR, which I have written here, is the relative molecular mass. Okay, so that is, it can be MR or AR depending on what we're looking at. If we're looking at just a single element or we're looking at a molecule. So what we're doing there is the relative molecular mass, or your MR, is the sum of all the relative atomic masses of all the atoms added to get together. And this is compared to 1/12 the mass of a carbon-12 isotope. Now, the definition does come up as well. As you can see, anything in red and italics, learn it. It's a 6-mark question. Okay, you get 3 marks for saying sum of the relative atomic masses of all the atoms in a molecule. The other 3 marks is for comparing it to 1/12 the mass of a carbon-12 atom, or you can say isotope. The reason they're comparing it to carbon-12 is we use carbon-12 as a standard. We use carbon-12 as a standard for everything. The reason why is it's high stability and it's high in abundance, so it's easy to work with. So that's why we use it as a standard. But just make sure that everyone knows how to calculate the MR. So let's say I have CO2, and I want you to ask me to find the relative molecular mass. To find the relative molecular mass, I go to the periodic table and I find the mass number of carbon, which is the big number of carbon, which is 12. I then find the mass number of oxygen, but I have 2 of them, so that's 2 times 16. And then I just add the 2 of them, and what I'll come out with is an MR of 44. So that means the mass of my carbon and my oxygen, my 2 oxygens and carbon dioxide, is 44. You need to be able to calculate the MR. Okay, now let's have a look at calculating moles of a substance. So remember what I was saying there, if you're given the number of moles, there's ways of calculating the moles. We'll go into that in a couple of minutes. But the one thing that I always find people struggle with is when you're asked to calculate the number of particles of something. So what they'll usually do at the end of a large question doing calculations is they'll ask you to calculate the number of atoms or the number of molecules. What they mean there is the number of particles, more specifically. So if they're asking you to calculate the number of atoms and the number of molecules, you straight away 2 things you need to do. If I see a number of atoms or number of molecules, I need to know my mole of my substance, which I have here. And 2, I need to use Avogadro's constant. Okay, that's all I need to know to calculate the mole or not the mole, to calculate the atom or the molecule. So the minute you see in a question, calculate the number of molecules, calculate the number of atoms, you straight away go, I need the mole of the substance, I need to use Avogadro's constant. So let's have a look at this question. By multiplying the mole, 1 mole of any substance will contain 6 by 10 to the 23 particles. So let's say I don't have a mole. We use 1 mole as a standard, but I may not always have a mole. So if 1 mole represents 6 by 10 to 23 particles of that substance, then what would 2 moles represent? It would be 2 times 6 by 10 to the 23. What would 3 moles represent? It would be 3 times Avogadro's constant. What would half a mole be? It'd be half times Avogadro's constant. So what we know is, we know 1 mole of any substance. It doesn't matter what the substance is. 1 mole of any substance will contain 6 by 10 to the 23 particles of that substance. So if I have 1 mole of carbon, that will be 6 by 10 to the 23. Therefore, if I have 2 moles of carbon, I will do 2 times 6 by 10 to 23. Okay, and that will give me my number of atoms. Okay, so you've got 6 by 10 to the power 20. We've got 6 by, yeah, so 6 by 10 to the power 23. Multiplied by 2, and we have 1.2 by 10 to the power of 24 atoms. Okay, so that's all you're doing. You're just multiplying by Avogadro's constant. Now, if they're asking you for the atoms, you write atoms afterwards. Now, let's go to the next one. It's 2 moles of oxygen. This time, I'm not dealing with an element, I'm dealing with a molecule. So I have the mole, and I multiply by Avogadro's constant. And again, I'm going to get 1.2 by 10 to the 24. But this time, I'm getting it as a molecule. So what I have there is 1.24 by 10 to the 24 molecules of oxygen. Now, this is where people get confused. If you're dealing with a single element, you're only going to ever be able to calculate the atoms because an element is made up of one type of atom. If they ask you to calculate the molecules or the number of molecules, you just multiply Avogadro's constant by the number of moles, and that gives you the number of molecules. But if they ask you to calculate the atoms in a molecule, the first thing you need to do is multiply. So I'll multiply 2 by 6 by 10 to the 23, and I find the amount of molecules there are. So I've got 1.2 by 10 to the 24 molecules of oxygen. Now that I know the amount of molecules there are, I can then look how many atoms are within that molecule. So if one molecule of oxygen has 2 atoms, then what will 1.24 by 10 to the 24 molecules of oxygen have? It will be, just multiply it by 2. So you just multiply it by 2, and we get 2.4 by 10 to the 24, 24 atoms of O2. So just be mindful when you're doing questions like this. If they ask you to calculate the atoms of an element like C or N or F or Na, all you do is multiply the number of moles by Avogadro's constant. If they ask you to calculate the molecules or to calculate the number of molecules, all you need to do of, let's say, O2 or F2 or Cl2 or N2 or H2O, all you do is multiply the number of moles by Avogadro's constants. But if they ask you to calculate the atoms of a molecule, you take the amount of molecules you have, and then you just multiply by the amount of atoms in one of those molecules. Okay, so that's why we'd multiply it by 2. Okay, now we're going to have a look at an empirical formula. What we have here is an example. So I'm just going to read through the example, and there's another question that you can practice in your own time. So the empirical formula, molecular formulas, empirical formula comes up quite a lot. I'd be very surprised if you didn't get one of these in your exam. It's a 6-mark question. It's relatively easy maths once you're able to do it. And 6 marks for very short a bit of maths to do is actually quite good. So we know what a molecular formula is. A molecular formula is relating to, so let's say we've got H2O2, okay? That's hydrogen peroxide. Okay, and what a molecular formula tells me is what type of atoms I have, hydrogen and oxygen, and it tells me how many of them I have. I've got 2 oxygens and 2 hydrogens. So that's a molecular formula. That's what we deal with all the time in chemistry. Now, an empirical formula is the simplest whole number ratio of a molecular formula compound. So let's say, for instance, you have H2O2. What that means is I have a ratio there of 2:2. So if I asked you to find the empirical formula of that, it's the simplest whole number ratio of that, which would then just be HO, because 2:2 is the same as 1:1. And we don't write H1O1. So what we can see there is the empirical formula is just the simplest whole number ratio of the molecular formula. So if we look here, calculating our empirical formula, we can see if a percentage is given, you can use it as a mass. So they may give it to you mass in grams, they may give it to you as percentage. You do it the exact same way, regardless if it's percentage or mass. So how you work out the empirical formula is you get your mass in grams or your percentage and treat it as a mass, and you divide it by the MR to get the number of moles. So we look here. I've got a mass of 75 for my carbon, and I have a mass of 25 for my hydrogen. I'm going to divide them by the mass number of carbon, which is 12, and the mass number of hydrogen, which is 1. And then what I've worked out is the number of moles. So remember what I was saying, your trusty old triangle? Your mass, your N, and your MR. So to calculate the moles, you divide your mass in grams by the mass number. So 75 divided by 12, 25 divided by 1. Now, what I've done there is I've got my moles, 6.25 to 25. That's the ratio. That's what is known as a molar ratio. So 6.25 to 25 is fine. That means for every 6.25 carbons I have, I'll have 25 hydrogens. But we don't deal in decimals or fractions, okay? We want it as whole numbers. So what I need to do is get them both into a whole number. So what I'm going to do is identify which of the two number of moles is the smallest. And as I can see, 6.25 is smallest out of that and 25. So I take the smallest ratio or number of moles and I divide both moles by that. Because if I divide 6.25 by 6.25, it gets me down to 1. And if I divide 25 by 6.25, it gets me down to 4. So that means that I have a ratio of 1 carbon to 4 hydrogens. So the 1:4 ratio is actually identical to the ratio of 6.25 to 25. The only difference now is we have it in a nice, neat whole number ratio, which means I have for every 1 carbon, I have 4 hydrogens. Okay, so I've given you another one there. You can practice using that method. See how you've got them as percentages? Treat them as mass. So that is 17.34 grams. That is 82.66 grams. And just treat them as a mass and find the moles. Okay, use your NMR triangle and then divide across by the smaller number of moles. Okay, it is a good one to practice. I'd be very surprised if you did not get a question like that on the summer exam. Okay, so now what we're going to do for the last couple of minutes, we've got about 20 minutes, 25 minutes left. I'm going to go through calculations with you in stoichiometry because you should have stoichiometry done in 5th year, absolutely, at this stage. I'm sure you're probably well equipped with it, but I do think the calculations always can pose a little bit of a tricky, and I can't emphasize how much you will be using stoichiometry through your whole Leaving Cert for different types of calculations. So it is really important. You will definitely have a calculation question relating to stoichiometry. So let's have a look. Calculating, the first thing we're going to look at is calculating the moles using the mass and the MR. So again, like I said, I have my trusty old triangle here. My mass is in grams. My MR is my mass number that you find on the periodic table of your substance. And your moles will always be represented by the symbol N. Now, you're given a balanced equation. I do this slightly different, so I'm just going to show you a method that will always make sure that you come out with the answer correct. So here we have is magnesium. We've got a balanced equation. You've got magnesium is going to react with oxygen to produce magnesium oxide, according to this equation. If a student burns 9 grams of magnesium in oxygen to ensure all of the magnesium reacts, calculate the number of moles of magnesium oxide. Now, at this stage, you should have done the moles. You should be well able to calculate the number of moles. But the difference is you're asked for the number of moles of the product and you have no information about the product. So remember, if you want to calculate the number of moles, you need the mass in grams and you need to know the MR of your substance. Now, I can find the MR of my MgO, no problem, but I don't actually have the mass of my substance. So I can't actually calculate it using my trusty triangle. But what I can do is, if it's a balanced equation, I can find the number of moles out about one substance in that equation, and I can then use that to find the number of moles about every single substance in that equation. So what we're going to do is I'm actually going to take that out for lack of confusion, just say in oxygen. So what we're going to do is I'm going to write out the balanced equation. Okay, so I've got 2 Mg plus O2 gives me 2 MgO. Now, what I'm going to do here is, what I will get is I'm going to highlight the reactant they've given me information on and the product they want me to get information on. So I've been given the mass of 9 grams of magnesium. So all I'm going to do is I'm circling magnesium. And the reason I'm circling it is because that is the one I have information on. And they want me to find the number of moles of magnesium oxide. So I'm circling the magnesium oxide. Now, the reason why I'm circling them is because I'm only working with the magnesium oxide. The oxygen in this is not relevant for my calculation. So that's why I'm circling, because I'm just focusing on those two. Now, like I said, I can't emphasize enough how much you need to be using this triangle. So what I'm going to do is, underneath my magnesium, I'm going to write M for mass. I'm going to write MR for my mass number. And I'm going to write N for my number of moles. Now, I was told I have 9 grams of magnesium. So where I have M written for mass, I write 9. The next thing I'm going to do is I'm going to go to the periodic table and find the MR, the mass number of magnesium, which if you go to the periodic table, is 24. Now, with that information, I have my mass and I have my MR. Look what I can do. I can calculate my number of moles. All I need to do is divide my MR into my mass. So I'm going to do 9 divided by 24, and I get the number of moles is 0.375. Okay, so what I've done there with one piece of information about magnesium is I've worked the number of moles of magnesium. Now, they didn't ask me for the number of moles of magnesium, but I need this number of moles of magnesium to find the number of moles of magnesium oxide. So now that I know the number of moles, what I go up to here is now I look at the ratio. It's not relevant when you're trying to find the MR or trying to find the number of moles at that point. It's when you're trying to transfer it to another substance. That is where you look at the ratio. Now, if you look at the ratio between magnesium and magnesium oxide, it is a 2:2, which is the same as saying a 1:1. Now, let's talk about that. What does that mean? It means that in this reaction, 2 magnesiums will produce 2 magnesium oxides. Okay? So if I had 1 magnesium, I would produce 1 magnesium oxide. If I had 4 magnesiums, I would produce 4 magnesium oxides. Now, I don't have 2 moles of magnesium. I have 0.37 moles of magnesium. So if I know that 2 magnesium will produce 2 moles of magnesium oxide, that means that if I have 0.375 moles of magnesium, I'm also going to produce 0.375 moles of magnesium oxide. So all you're doing with the balanced equation is you work out information about one of them, and then you use that and transfer it into information about what you want or whichever substance you want. So there, what I've done there is I have found that the number of moles of magnesium oxide will also be 0.375. So then right at the end, I'll just write 0.375 moles of MgO. Okay, so you can see the transfer using the M, the MR, and the N underneath the element or the substance you have and the substance you want is a really, really good way to ensure that you don't make any errors. You're able to transfer them over. Okay, another thing to note, if you're ever in doubt, find the number of moles. Okay, the number of moles in chemistry is the foundation to find any value relating to that substance, whether it be the volume, whether it be the mass, whether it be the relative molecular mass, whether it's the concentration, whether it's the I think what else is our concentration, whether it's the pressure or the volume if you're using ideal gases. You need the moles for nearly everything to find the values out about a substance. So if you're ever unsure about a question, find the number of moles because it is a stepping stone to find the rest of the answer. Okay. So we're going to have a look at the next one. This time, instead of calculating the number of moles, I'm calculating the mass from the moles. So again, trusty old triangle, still using this. Okay, now I'm using the same equation. So I've got 2 Mg plus O2 will give me 2 MgO. And what we can see here is magnesium will react with oxygen to produce magnesium oxide according to the equation. Again, if a student burns 9 grams of magnesium in oxygen, to ensure all of the magnesium reacts, what mass of magnesium oxide will be formed? So we could actually just use what we had in the other part, but again, I'm just going to do it as a stepping stone. So I'm circling the one that I have information on, and I'm circling the one I want information on. Now, what I'm going to do is underneath the one I have information on, I'm going to write N, MR, and N. And I'm going to fill in what I have. So I have my mass, which is 9. My MR we found on the periodic table is 24. And if I divide M by MR, I'll get 0.375. So I now know the number of moles of my magnesium, even though that's not what I want. But because it is a 2:2 ratio, if I have 0.375 moles of magnesium, I must also have 0.375 moles of magnesium oxide because it's the same ratio. Okay. So again, I write my M and my MR. Now, this time they're asking you to calculate the mass of magnesium oxide. So we're looking for the mass here. So this time I'm looking for my mass. So for me to have my mass, I need to know my number of moles, which we figured out because we were able to transfer it over. And I need to know my MR. So your MR magnesium, Mg is 24 and oxygen is 16. So the MR will be 40. So your MR is 40. Now, how do we calculate the mass? All you do is you take your number of moles, which is 0.375, and you multiply by the MR, which is 40, and we find the mass is 15 grams. So remember, the mass is always given in 15 grams. So then all I do is 15 grams of MgO. Okay, so again, all you're doing there is you're ensuring that you're transferring it over. Now, you may have learned this in different ways, and that's absolutely fine. But I do find that this way is a really, really good method. I feel like it's a method that you just really are unlikely to go wrong with. If stoichiometry and balanced equations are a bit of an issue, this is a way that you should definitely go with, because you have all of your information laid out for you there. Okay. Right, so we're going to continue on the calculations. So I'm going to come back to this one because this one takes a bit of time. What we're going to do is we're going to now look at calculating the volume calculating the volume of a substance from the moles and STP. So look, some of you at this stage may have done ideal gas, but I do know some teachers actually leave ideal gas to 6th year. So if you haven't done ideal gas, you may not have been introduced to STP. If you have done ideal gas, you would know STP stands for standard temperature and pressure. Now, the standard temperature and pressure just means that we have a standard temperature and we have a standard pressure. We also actually have a standard volume. And when let's say our gas is at a standard temperature and pressure, it will occupy a volume of 22.4 liters. Now, you need to be familiar with your STP is 22.4. It is in your log tables and it is given to you on the day of the exam. So you don't need to learn it off, but to be honest, you'll get used to using it. So STP is the volume that a gas will occupy when it is at a standard temperature and pressure. So it's 22.4. So 1 mole of gas will occupy 22.4 liters. But remember, we don't always have 1 mole. We might only have 0.5 moles. We may have 2.5 moles. So remember that if 1 mole of any gas will occupy a volume of 22.4 liters at a standard temperature and pressure, then if I have more than 1 mole or less than 1 mole, I just need to multiply that number of moles by 22.4 to find that volume, okay? And this is a question that always is posed in balanced equations. So how you do this is we've got our carbon and our oxygen, and we have our CO2. Now, the question says, and it will always tell you, it won't expect you to know when to use STP. It will give you that hint. It will say at STP or brackets STP, okay? So it's asking you to calculate the volume of carbon dioxide at STP when we have 20 grams of carbon burned in oxygen. So again, like I said, what I'm going to do here is I'm going to circle the one I have information on. So I've been told I have 20 grams of carbon, so I'm circling that one. And I want information on my carbon dioxide, so I'm circling that. Now, you're going to see what I'm going to do here. Okay. Now, if you look at the question, I have a mass of carbon of 20 grams. So I have to use this for the carbon. So I'm going to write N, MR, or AR for carbon, and N. Now, you'll see AR is the right one for a single element. MR is when you're dealing with the molecule. I just get into the habit of just writing MR. So we have a mass of 20. If we go and find the mass number of carbon, it is 12. So then how do I find my number of moles? All I'm going to do is do 20 divided by 12. So your mass divided by your MR. And I come out with the number of moles of 1.6. It's 666 recurring. So I'm just going to use 1.667. Now, another thing to note, do not round too early. If you are using the number of moles for another part of a question, you really should be trying to do it as long as you can. Usually what I'll do, which you probably can't see, is I leave mine on my calculator, and then if I need to use it for something else, I'll multiply it by something, then I'll just multiply it straight by the calculator, okay? If you really want to, you can round it to 3, really 4. The longer you have it, the more accurate it's going to be. When you get to the end of a question, then you round up to 2 to 3, that's fine. But when you're trying to do the question and you're leading it into another, the more accurate it is, the better. Okay, so what we can see here is I found the number of moles. There's different ways of finding the moles. This is one of the ways, probably the most common way. When you have a mass and you have the MR, you can find the moles here. The next thing I'm going to do is I'm only looking between my carbon and my carbon dioxide, which is a 1-to-1, meaning 1 mole of carbon produces 1 mole of carbon dioxide. Therefore, 1.67 moles of carbon must produce 1.67 moles of carbon dioxide. So what I've done there is I've written my number of moles. The next thing I do is I write this as V and STP. Now, I know the molar volume in STP is 22.4. And I'm looking for my volume, okay? So what you'll know is, remember what I said, 1 mole of any substance or 1 mole of any gas will occupy a volume of 22.4. So what if I had half a mole? What would you do? You'd multiply half by 22.4. What if I had 2 moles? You'd multiply 2 by 22.4. So when you're trying to find the volume of a substance at STP, you need to multiply the number of moles by STP. Or if you want, I'll give you this, you don't have this triangle, but if it makes it easier for you, you could do it like this. Sorry. So there's another triangle. It might make it a little bit easier because sometimes you may actually have the volume. They want you to find the number of moles. So there's another trusty triangle you can use for volume, moles at STP. So what we'll do is we'll go down, and all I need to do is to find the volume. I just need to multiply my number of moles by STP. So that would be 1 point. And like I said, I kept this on the calculator now. So all I'm going to do is multiply my 1.667 by 22.4. And I get the volume of 37.33, and it's in liters, okay? Because our molar volume of STP is in liters. So then all the question was asking, sorry, we go back up. It said, what was the volume at STP of our carbon dioxide? So we would say that we have 37.33 liters of CO2 at STP. Okay, so that's all I've done there. So remember that it is in liters because your STP is 22.4 liters. So then when you multiply it by the moles, it gives it to you in liters. Now, we're not doing this one, but another one you can use. Sometimes they won't use STP. Sometimes they might say RTP. And RTP is just another standard, okay? It's a standard, but this time it's at room temperature and pressure. Now, a gas will occupy a volume at room temperature and pressure of 24 liters, okay? Very similar. The difference is you're given STP in the exam, you're given it, it's in your log tables, you're not given RTP. So you need to learn RTP, okay? RTP is a lesser one. They don't ask it as often, but they can ask it. It is done the exact same way as STP. You just multiply the number of moles by the molar volume at RTP or STP. Do not get them mixed up if you can. So 22.4, your STP is in your log tables, given to RTP, you have to learn. Okay, so we're going to go through that question. It's a Leaving Cert style exam question at the end, but I'm just going to come up to this one now. So some of you may have come across this question before. Some of you may have not. So you're asked this time to calculate. So I'm just going to get this here, moles, N, and MR. So you're asked to calculate the MR this time. Okay, so it's a little bit different because you're used to being able to find the MR. You go to the periodic table, you add up the mass numbers, and you can use the moles or the mass to find the other one. This time you're asked to calculate the MR. So you actually need to know the mass and you need to know the number of moles. Now, why would you ever need to calculate the MR? It's when you don't know specifically how many substances are within an element. So here we have sodium sulfate, that is a salt. It's a hydrated salt. How do we know it's hydrated? Because it has water molecules attached to it, okay? So they may use sodium sulfate, they may use carbonate sulfate, they may use potassium sulfate. It doesn't matter what salt they use, but how we know which one is a hydrated salt, you'll see H2O attached to it. Now, they'll say the anhydrous salt. So if this is a salt that's hydrated, this is the salt that has no water. Anhydrous means it does not have the water, okay? Apologies, I should have written it like this. So what we can see is a chemist took 3.22 grams of hydrated sodium sulfate crystals until there was no loss in mass occurred. He found that 1.42 grams of anhydrous salt was obtained. Calculate the formula of the hydrated salt. So, okay, so the first thing we're going to do, this is a tricky one to kind of get your head around. So the first thing we'll do is we'll do Na2SO4.XH2O. And that is heated and it's broken down into just its salt without the water. And there's the water that obviously had evaporated. Okay, well, that should be XH2O. Now, there's loads of different ways of doing this, okay? But what we're going to do is we're going to work with the information that we do have. we're given 3.22 grams of the hydrated sodium crystals. So I'm going to write my mass there is 3.22. Sorry. And I'll write my MR and I'll write my number of moles. Okay, but I don't know the number of moles and I don't know the MR, so I can't work that out at this point. But I have been given information on the anhydrous salt, i.e. remember anhydrous is without water. So same salt minus water. Sorry, without water, not without salt. Apologies. Okay. So I have a mass of my anhydrous salt as 1.42. I can work out my MR because I know that whole substance. So sodium, if you go to the periodic table, is 23, and I have two of them. So that's 23 plus 23. Sulfur, if you go to the periodic table, the mass number is 32, so that's plus 32. Oxygen, if you go to the periodic table, is 16, but I have 4 of them, so that'll be plus 4 times 16. And I will come out with an MR of 142. Now, look what you can do there. You have your mass, you have your MR. So what can I work out? I can work out my number of moles. So it'll be 1.42 divided by 142, and I come out with 0.01 moles. Now, look at this. It is a 1:1 ratio. So what I can do is, if I have 1 mole of my anhydrous salt was produced from 1 mole of my hydrated salt, then 0.01 mole of my anhydrous salt would be produced from 0.01 moles of my hydrated salt. So what I've done there now is I found the number of moles. Now look at what you've got here. You have the moles, you have the mass, so now I can calculate the MR of my substance. Okay, so all I need to do is divide my mass, which is 3.22, and divide that by 0.01, and I come out with an MR of 322. So now what we're going to do is we're going to work with this. So my Na2SO4, which is hydrated in X amount of water molecules, has a mass number of 322. But I don't know what X is. That's what I'm trying to do. So I'm just going to note here, Na2SO4 dot X H2O is the same as saying Na2SO4 plus H2O. Okay, that dot is not like in maths, it's not multiplication. That means that we have an addition of a certain amount of water molecules that is hydrating the salt. So that is the same as writing that as plus. So I can write that as equal to 322. Now, the next thing I'm going to do is I can find the MR of my Na2SO4 just on its own. I already did. I did it up here. So I know my MR there is 142. Now, I don't know how many water molecules I have. I have X amount of water molecules, and we're trying to find X. So what I can do is I can work out the MR of 1 water molecule, and it's 18. So if that's 18 times X, then it will be 18X. Now, all you've got there now is a nice linear equation. So what we have there is 142 plus 18x is equal to 322. So it's a linear equation. What do? We want to find x. We need to isolate x, get x on its own. So the first thing I'll do is I'll move my 142 over. So I'll have 18x is equal to 322 minus 142. So we will have 18x is equal to 180. And then how do we isolate it? If it's 18x and we want to get 1x, I just need to divide my 180 by 18. And I find that x is equal to 10. So what we've done there, by using the number of moles of one substance and transferring the number of moles over to the substance we're looking for, using the moles and the mass that was given us of this substance, we could work out the MR by using our trusty triangle. And then all we need to do is create it like a balance or an algebraic equation. So what you need to remember is if you ever see a molecule that has dot XH2O, or it could be dot 10H2O, dot 9H2O, that means it's Na2SO4 plus a certain amount of H2O. So then you would just write it as Na2SO4 plus XH2O, and that equals a total mass number of 322. Once you get to that, you're doing a certain linear equation. So then my actual formula at the end will be Na2SO4 dot 10H2O. Okay. Now, what I'm going to do is, I know we're kind of running into our last couple of minutes. So if anyone needs to leave, by all means do. I will have the booklet ready for you if you want to get it off. If you I think you're able to request it on Monday. But what I'm going to do is, I'm just going to go down. So anyone that is staying and has covered stoichiometry extensively, I'm going to go through a Leaving Cert style exam question where it actually covers all the calculations that you may be asked. So if you are free, and I know we're kind of running over time, but if you are free, please stay on and I'll continue going through this question. So you may get a question, like I said, if you've done stoichiometry, I'd be very shocked if you haven't done stoichiometry at this stage. It'd be very unusual to be doing it in Leaving Cert. So you should, or to be doing it in 6th year. So you really should be able to do your stoichiometry or have practicing your stoichiometry. But what I'm going to do is, I'm going to show you what exactly, this is very much like what an exam question would actually look like. Okay, so we have there is where you're asked multiple different questions relating to one balanced equation. So when calcium carbonate, CaCO3, reacts with hydrochloric acid, calcium chloride, water, and carbon dioxide are produced. The following equation is given to you. A student reacts 10 grams of calcium carbonate in excess hydrochloric acid. Calculate the number of moles of calcium carbonate used. Use the balanced equation and calculate the mass of the calcium chloride. Calculate the volume of the carbon dioxide produced at STP, and lastly, calculate the number of molecules of carbon dioxide. Now, if you're able to answer this question, you should be fine with any stoichiometry questions that are thrown your way. Some of you may have done stoichiometry too. Most teachers leave it till 6th year. So if you have, you may have to then do obviously limiting in excess. Otherwise, this is what you'll be looking at. So we'll have a look. We've got calcium carbonate plus 2HCl. So you see what I'm doing here? I always write out the balanced equation when I'm doing calculations, because I'm going to be writing underneath this. First, I'm going to highlight what information I need or have, and then I'm going to write underneath it whether it's the mass, the moles, or whatever I need from it. So the first thing I'm going to do is I'm going to circle the ones I have information on and circle the ones I want information on. So I've been given 10 grams of calcium carbonate. So straight away, I already know I have information on this. I'm asked about calculating moles for calcium carbonate. I'm asked about calcium chloride, so I circle that. I'm asked about carbon dioxide. And that's it. That's what I'm asked about. They're the 3 that I'm asked about. Now, again, the reason why I'm doing this is now look what I'm doing. I've got a 1:1:1 ratio. I'm only looking specifically at them. So what I can see is I have a mass of 10 grams of calcium carbonate. So what I'm going to do, again, now you're probably sick of me saying it, but I do write this all the time because it's really important. So because I have a mass, I'm going to use my M, my MR, and my N. Okay, so the mass is 10. I need to work out my MR of calcium, or calcium carbonate. So we've got carbon is 12, 3 times 16, and our calcium is 40. So when you add all of them up, we come out with an MR of calcium carbonate is 100. Okay, so if I want to find my number of moles, because it's asking me to calculate my number of moles, all I need to do is do 10 divided by 100, and we get 0.1. Now, what I'm going to show you here is that, so you're going to be using this for the next part, but all I'm going to do here is I'm just going to write beside that A, because what I've done there is I've already answered that question. I've found A. So the next thing I do is I'm asked about calcium chloride. What are we asked? We're asked to calculate the mass. So this time, I need my mass. So I'm going to write my M, my MR, and my N. Okay, and we have the MR of calcium chloride. So you've got chlorine, which is 35.5 plus 35.5, which is 71, plus calcium, which is 40. So we get an MR of 111. Now, just to note, in case any of you didn't know this yet, when you're finding the MR of your substances, remember you round, okay? So calcium is 40. It might say 39.999 on the periodic table, you round that to 40. Calcium, if it said 11 point, or if it said carbon said 11.999, you'd round that to 12. But when you're talking about chlorine, it's always taken as 35.5. So you don't round chlorine, you always keep it as 35.5 because I have 2 of them, that's 71. So I have the MR there, I've worked out the MR. I'm looking for the mass. So I need to know the number of moles. Now, I know 1 mole of calcium carbonate produces 1 mole of calcium chloride. Therefore, 0.1 mole of calcium carbonate would also produce 0.1 mole of calcium chloride. So then all I'm going to do is I'm going to multiply. So what we got, multiply our 111 times by 0.1. We have we have 11.1. So again, what I've done there is I found the mass. So I'm just going to write B beside that. Okay, now the next part of the question asks you to calculate the volume of carbon dioxide at STP. So remember, what I'm going to do here now is I'm going to write V, I'm going to write STP, and I'm going to write N. Because to calculate, and this time, there's your little triangle, it's V and N, STP. In STP, we use the molar volume of 22.4. So I already know that. Now, for me to calculate the volume, I also need to know the number of moles. Now, the number of moles I don't have, but again, it's a 1-to-1 ratio. So if 0.1 mole of calcium carbonate produces 0.1 mole of calcium chloride, it's also going to produce 0.1 mole of my carbon dioxide. So then all I need to do is 0.1. So it's N times by STP, or molar volume at STP, which is 22.4. And I come out with a volume of 2.24. And I just write liters. Remember, that's liters. And then I write C beside that. Okay, so there are your first 3 questions already done. Now, lastly is to calculate the number of moles of carbon dioxide. So remember what I said. If it says calculate, the number of molecules, you need the moles and you need Avogadro's constant. And all you do is multiply moles by Avogadro's constant. So we already found the moles here. It's N. And I'm just going to write Avo for Avogadro's constant will be 6 by 10 to the power of 23. So what I do is I multiply 6 by 10 to the power of 23 times by 0.1. Oh, sorry. 0.1, and we get 6 by 10 to the power of 22 molecules. Okay, because you're only asked, we know carbon dioxide is a molecule. So to find the number of molecules, you just multiply the number of moles by Avogadro's constant. Now, if I asked you then to find me the amount of atoms of carbon dioxide, I look at how many atoms are in CO2. For 1 carbon, 2 oxygens, so there's 3. So if I have 6 by 10 to 23 molecules of carbon dioxide, then multiplying that by 3 will tell me the amount of atoms I have of carbon dioxide. Okay, so unfortunately, we didn't really get, I wanted to go on to chemical bonding, but obviously we didn't get we didn't have sufficient time to go on to it. But what you will be asked, obviously, in questions is your atomic theory, definitely, your electron arrangement, definitely, stoichiometry, mole concept, calculations, definitely. I would expect chemical bonding as well. So what you really should be doing is, we'll just have a quick look there. You need to obviously know the difference between ionic bonding, covalent bonding. You need to know your characteristics around ionic bonding, okay, and covalent bonding. So remember, ionic is stronger than covalent. Ionic can conduct electricity when in molten or liquid or in solution because their charged ions can move. They're high melting and boiling point because they're quite strong. Covalent, on the other side, they're lower melting points and lower boiling points because they're weaker than ionic. They don't conduct electricity. They're usually smaller molecules. And you do need to be able to draw the dot cross diagram around both of them. You then will obviously have intermolecular forces around covalent structures. You have your molecular geometry. You would definitely need to know all about your tetrahedral, your pyramidal, your trigonal planar, all the different shapes that you will have. Now, because we didn't obviously get to go through those ones, I do have like a few notes on them that again, if you request them, you will be sent them out on Monday. So you will have access to any of the topics that we didn't get covered and any of the other little bullet points that I have on what you should be covering. But really, they're topics that you should be going through: chemical bonding, stoichiometry, mole concept, the atomic structure, the electron arrangement, and also periodic table. You would definitely have covered periodic table and trends in the periodic table. They're the ones that you really should be focusing on. But chemical bonding and stoichiometry and the atomic structure, I think, will be big ones to have a look at. So we'll stop there because I know I've gone over, and I'm sure all of you are dying for a little bit of a break. So thanks a million for everyone that's joined. I'll stay on. If anyone has any questions that they want to ask, by all means, you can stay on and you can just send chats in, because I'll stay on with you for the next couple of minutes. Otherwise, if you don't have any questions, make sure that if you do want to request the notes, that you do let David know, and I will make sure to get the notes to you. And obviously, you can watch back the recording whenever you need to. So thanks a million for joining, and hopefully see you again soon. Hi, Loria. Do you have a question that you want to ask? Okay, so we've got a few questions or hands coming up in here. So for those that have their hands up, do you want to just write into the chat? Because I know you're obviously muted. So if there's anyone that wants to write into chat, if you have any questions that you want to ask. Michelle, I see you have your hand up there. Can you write into the, are you able to write into the chat? So do you see the chat up here? So I don't think that you're able to unmute yourself. So if you can give me a little message into the chat or the Q&A even. Actually, I think there's a Q&A there as well. Okay, so I'm just having a look at, just bear with me a second until I get the Q&A up. The can you go through the best way to study for and get good at question 5, please? Now, are you talking about question 5 in the Leaving Cert? So what you're looking at there is you're looking at atomic structure, electron arrangement. So there are two of the things that you would actually be. So what we went through there, the atomic structure, the electron arrangement, they would be in question 5. Chemical bonding is also in question 5. So would be ideal gas and radioactivity. So it really depends on the way that the questions are posed at you that year. But what we've covered there in terms of the atomic structure and the electron arrangement, that is exactly what you would get asked. So anything relating to the electron arrangement, where you're talking about emission line spectrum, you'll be talking about the only one I've ever seen them ask about the Bomber series, but they will just ask you, it will always about the electrons going from excited state down to going excited state down to ground state. If you actually list out those little steps that I've done, that's exactly what you should be studying for the electron arrangement part. When it comes to the atomic structure part of question 5, you should really also be studying the history of the atom. They will always ask about Thomson Rutherford. I can't emphasize enough how much they go into the two of them in details. So when it comes to those, that's what you really should be studying. As for the rest of them, in terms of ideal gases can sometimes be thrown in it. Ideal gases can also be in a different question. If you have ideal gases, and let's say you have covered ideal gases with your teacher, a lot of people don't do it to 6th year, but let's say that you have, what you really need to be focusing on is PV is equal to nRT. Now, I know some you may use books, and you might notice in books there's two equations. There's a combined gas law equation. I wouldn't really be using that. I'd be sticking with PV is equal to nRT. And there's two reasons why I stick with PV is equal to nRT. One, you have it in your log tables, so you don't need to learn it off. Okay, PV is equal to nRT is an equation that's given to you, so you don't need to learn it off. Second of all, sometimes they actually specifically ask you to use PV is equal to nRT. So if you're asked to use it, it's better to use that method. So you need to be able to use the ideal gas equation. Now, when it comes to the ideal gas equations, there's something that you have to be able to do. You need to know the units of your PV is equal to nRT. Your pressure is always in pascals, okay? Your volume is always in centimeter or in meters cubed. Your temperature in gases are always in Kelvin. Now, if you are able to convert very easily between kilopascals and pascals, meters cubed and centimeters cubed, you should have no problem doing the equation or using PV is equal to nRT because it's only substitution. So that's the kind of question you will always get asked in terms of calculations. The next thing that you do in terms of ideal gas that you should be covering is just the limitations. So we know ideal gas, there's 5 of them we talk about, but there's 2 that don't actually fall in, that kind of are deviated away from ideal gas. You're always asked about the 2. So you need to ensure that you're able to answer the 2 deviations away from the ideal gas. So that's the other thing that you should be looking at. Now, in terms of radioactivity can also be thrown in there. And if radioactivity is thrown in there, again, it's very short. You really just need to know what the properties and characteristics are of alpha, beta, and gamma. You need to know the penetrating power, which is stronger, which is not stronger, or which is stronger, which is weakest. You need to give real life examples about the 3 of them, whether they're used in, like radiotherapy, or they can be used in the smoke alarms, that kind of thing. And then lastly, you need to be able to write a nuclear equation, which are relatively straightforward. And that's essentially all you would need to know in terms of radioactivity. Then you go on to periodic table. That can also be thrown in. Periodic table, when in terms of periodic table, that's thrown into question 5. Again, it's like the atomic structure. You need to know about the history of the periodic table. Mendeleev is really important. The modern periodic table, they pose an awful lot. What they're likely to ask you in relation to the periodic table is give 3 to 4 differences between Mendeleev and the modern periodic table. That comes up all the time, okay? So you want to know 3 to 4 differences between them. When it comes to any of the other scientists, say like Dobriners, triads, or you're looking at the law of octaves, you just need to learn the definitions. That's all you need to know. So any of the other scientists, just learn the definitions of their contribution. But when it comes to Mendeleev and the modern periodic table, you need to know the differences between the two. So remember, what we talk about Mendeleev is he left gaps in the periodic table and he predicted unidentified or elements that had yet to be discovered. That's the kind of thing that you'd be asked about in the periodic table. Then you go into obviously trends in the periodic table, but that's a different section. That's a usually different question. And then obviously your electron configuration, which we already went through. So because question 5, you know, they really can snip it between it. The most of what I do see in question 5 will be the atomic, the electron arrangement, hence why I went through them today. Then the periodic table, again, history of the periodic table. Like I said, just study Mendeleev, the modern periodic table, and learn the definitions of the rest of the scientists. And then radioactivity, like I stated, just know the two, just know your penetrating power and your examples and be able to do nuclear equation. Okay, that's essentially how you will get good. Now, the other thing that I will always suggest for any of you that are still on and thinking about this, if you have study clicks, use it. If you don't have study clicks, get it, okay? Because it is a really, really good example of how you can actually continuously practice the questions, okay? You'll have on a question, anyone that won question 5, you will be able to access question 5. Just go into the atomic structure, you will see it there. Or you can go on to examinations.ie and go into past exam questions. And if you want to just focus on one specific question, like you're saying there that you wanted to focus on question 5, you can do those and you have the solutions or the marking scheme to go through them. You will notice the more practice you get in doing the exam questions, how similar questions are. They may be posed differently, but the questions are always repetitive. They may maybe worded slightly different, but the answers are always identical. So anything that I've given you today in bullet points, that is the way that you should be learning it, because that is exactly the way that they're going to ask it. Definitions, learn them off and learn them properly. Don't reword them, write them the way that they're asked, because it's really important. Okay. Okay, I'm just trying to see, do you have any tips on understanding, learning the trends in the periodic table, or does it come up a lot? Okay, so trends, you know what, when it comes to trends in the periodic table, it's always very tricky, okay? What you would be doing is, it depends on what the trends is. So like you're looking at the trends, there's the electronegativity, for instance. That's one trend on the periodic table. Ionization energy, that's another trend that you need to be looking at the periodic table. And then the atomic size. So really there's not necessarily a tip in terms of like how you learn it. You really have to try and understand the foundation around it. So electronegativities, let's take that for instance. If you're unsure with electronegativity and they ask you about the trend, what you can always do is a little bit of a cheat sheet, is go to Linus-Pauling scale. Okay, if you cannot remember which is more electronegative, which is less electronegative, you can go to the periodic table and then find, or not the periodic table, go to your log tables and go down and find Linus-Pauling scale on the log tables, and they will give you the electronegativity values. You'll see the higher the electronegativity value, the more electronegative something is. So if we talk about trends on the periodic table, for instance, and you're talking about electronegativity, the further you go to the right and the further you go up the periodic table, the higher the electronegativity. Now, what does that mean? It means that those elements or atoms of elements that are further to the right of the periodic table and higher up will have a greater pull of the electrons towards them. So the electrons are more attracted to them. So fluorine is the most electronegative. Okay, so when it comes to the trends relating to electronegativity, what you should be doing if you get confused is go and look at the Linus-Pauling scale, and you can see which one is more electronegative. When it comes to, say, the atomic size, these questions, Ella, they don't appear an enormous amount, but they can. So this is one question you may have come across, and I actually wouldn't be surprised if your teacher put it in, because I put it in a last summer test. So there's a question where they might give you 2 elements, and they'll ask you, if you use this element, give me another element in this group that is larger, or give me an element on this period that is smaller. So remember, you've been talking about atomic size. If we go down a group, we expect the atoms to be bigger. Most people find that relatively straightforward, because as you go down each of your groups on the periodic table, what do we know? There's more and more electrons, but there's more and more shells. Okay, our groups, as we go further down our group, we know that there's more and more shells. So if there's more and more shells, the atom's getting bigger and bigger and bigger. So we know the further you go down the group, the size of the atom gets bigger. Now, as we go across a period, a lot of people are like, oh, the atom also gets bigger because they have more electrons. But that's not true, because what do we know about what periods are? Periods tell us the amount of shells that our atoms may have. So if we have, say period 3, all of those elements in period 3 have 3 shells. So it doesn't matter that they actually necessarily, like one of them might have more electrons, they're still going to have the same amount of electrons, or they're going to still have the same amount of distance from the nucleus. So you think about it, even as we go subsequently across from right, let's say across period 3, what you will notice is that each one has a new electron, but it also has a new proton. So as we keep going across, we have more protons, we have more electrons, so there's a bigger attraction. But what we're noticing is it's still in the same shell, so it's not getting further and further from the nucleus. So what you're actually noticing is the attraction between the positive and the negative is so strong that it actually pulls the electrons towards it and makes the actual atom smaller. So when you're asked about trends in the periodic table, I'll give you, this is the tip that you really need to know. The 2 things you always mention, doesn't matter what the trend is, you always mention shielding, or you can call it screening, and you always mention the shielding and screening. You mention the oh my god, what's my actual losing it? Yeah, the shielding, the screening, the atomic size. Yeah, your atomic size. Okay, so if you're talking about shielding and screening, it means that are the electrons in the outer shell going to be attracted to the nucleus? What would affect that? What would affect that is if you have more electrons in between, they're being shielded from it, okay? Also, the more shells there are, the further the distance from the nucleus. Sorry, the distance is what I was looking for. So the 2 things that you should always mention, the distance from the nucleus and the shielding. So when you're trying to learn the tips, or you want tips around the trends on the periodic table, what I want always, doesn't matter what the trend is, always talk about shielding, screening, and always talk about the distance from the nucleus. But when you're thinking, you have to really think about it, okay? If there's more electrons and there's more shells, the electrons in the outer shell are further from the nucleus. The further they are from the nucleus, the weaker the attraction. So therefore, the bigger the atom is actually going to be, the easier it is to remove the electrons. But the less shells that we have, the closer the electrons are going to be to the nucleus, because they're being pulled towards it. The attraction is greater. So always talk about screening and distance from the nucleus, Ella. But again, it doesn't come up an enormous amount, but that doesn't mean that it won't come up, Ella. Okay, Sophie, so you're on to volumetric analysis. That's a tough one for you now. Does it come up a lot, and is it specific experiments, or is there a choice? Well, look, for summer exam, I don't know. It's completely up to your teacher whether she gives you it gives you a choice. But in the Leaving Cert, there's absolutely choice. So you have 11 questions. You have to answer any 8. So you do have quite a bit of choice. You can leave experiment questions off. So you're talking about volumetric analysis. I'm assuming the volumetric analysis you're talking about is concentration. So you're looking at your acids and bases rather than your oxidation and reduction. Maybe you're talking about both. Do they come up a lot? Yeah, they do. They're huge. Okay, so because you have such a choice in the Leaving Cert, you can leave off. But think about it, you have to answer 8 questions out of 11. The first 3 questions are experiment questions. So if you leave the 3 of them off, that's fine. You don't have to answer any questions on the experiment, but that means that you have to answer every other question from section B. So that's all the theory. You don't have a choice. I would always suggest students to make sure that they are able to do a question relating to an experiment. And I think with volumetric analysis, it's very, very repetitive. Again, if you notice the stoichiometry questions we did today, it's pretty much like that, but then they just add concentrations and molarity. That's the only thing we haven't done, because usually don't really do it till 6th year. So it's the same kind of method. The way that exam question I gave you, it's laid out very similar to that in terms of calculations. They just do one step further. They just ask you to calculate the concentration from the moles, or they'll ask you to calculate the volume or ppm. They're the kind of other things, but they're very similar to what we've just covered. In terms of experimentation, if you notice a volumetric analysis, it's all titrations. They're always the same. So the questions that they'll ask you around the actual experiment is the same thing. It's always generic. They'll ask you, how did you set up a standard solution? How did you clean out the burette? How did you clean out the pipette? That's the kind of questions that they would ask. So I would, unfortunately, because we won't get through volumetric analysis now, and I don't know whether your teacher's giving you choice for the summer, but in the Leaving Cert, you will have ample choice. So if you do want to leave the question off related to volumetric analysis, you actually can. But in my opinion, I wouldn't. If you like stoichiometry, or if you're able to do stoichiometry, I think practice volumetric analysis, because you will eventually see how repetitive the questions become. Okay, so going on to our next one there with Sophie. I don't know if that's I or L Kavanagh. So how would you go about studying experiments? Again, I would tell you, when it comes to the experiments, I would be going to study clicks. That's where you're going. Okay, because if you will see that they have actually separated the experiments out into threefold. Okay, you've got your first question, which is based on your titrations. Your second question, which is based on organic chemistry. Your third question is a miscellaneous of the rest of them. So going about studying for the experiments, if you can just continue and go through all the exam questions, you will actually see the style of questions that they ask. And then you will see that what you actually need to be learning from the experiment, because you don't need to know everything from the experiment. You don't need to know step by step procedures, but you do need to know outlines, and you need to see the type of questions that they'll ask. And I promise you, you'll see a pattern. It will always be a pattern. So for the likelihood, you do a lot of titrations. You do an enormous amount of titrations. They're not going to specifically always ask you about titrations of every specific experiment. What they will ask you is to explain how you carried out an experiment. Like I said a minute ago, how would you clean the burette? How would you set up a standard solution? How would you, when you're reading the burette, you read from the bottom of the meniscus. It's the same questions over and over and over. The one thing that you should know per question is endpoints. So if you've done titrations, you will need to be able to, you might get asked questions specifically about an experiment where, what was the endpoint color? What did it change from? It went from red wine color to blue black, or blue black to red wine, whichever. It went from a yellow straw color to colorless. That's the kind of thing that you would need to do. But I can't stress enough, study clicks, go to the experiment ones, and they will have them laid out, and just continue to, you don't even need to, you just read through them, read through the solutions, and then see how many times the questions just repeat themselves over and over and over. That is the best way to go through your experiment questions for studying. Okay. Olivia, sorry, in a question relating to Ernest Rutherford experiment, would they specify if it's a conclusion or observation they're asking for? That's a really good question. So when you're talking about it, Rutherford, they will actually want both. They may not necessarily specify. Sometimes I have seen them and they were like, what would they do more? It's not necessarily observation and conclusion, because his observation is essentially his conclusion. They might say prediction and conclusion. So basically what they mean is what did they expect to happen and what actually happened. And what actually happened then made them conclude that, the atom was made up of mostly empty space, or so on. So really what you need to know is what they expected to happen. They expected that most of them will be deflected at large angles because it's all positive and negative everywhere. But then what did actually happen? And then you would say what happened was most went through, some were deflected at large angles, and some came straight back. And then you say your conclusion. That means that it's mostly empty space. That means that the positive nucleus is very small and concentrated. So yeah, they can ask you for the prediction, and then they can ask you for the observation or the conclusion, or they might actually give you the predictions and they might say, how did Rutherford's experiment deviate away from that? That's the kind of way that they would ask the questions. So the things that I gave you, that's what you just learned. That's all you need. Okay, just learn what actually happened, and then what's the conclusion from that about the atomic structure. Okay. I think is that we still have, sorry, is Bilal, are you still there? Okay, so I don't know if you're still there, because that was a couple of minutes ago. I only saw that. Someone's asking about the dot cross diagram. Let me see if you're still there. No, I don't think he's still there. Okay. If anyone was talking, or like, let's say for instance, your chemical bonding. I will have so anything that we did not get through today, because obviously we only had an hour and a half. Anything we didn't get through today in terms of like chemical bonding and stuff like that I was going to go through. I do have a step-by-step of how you actually do your dot cross diagrams for ionic and covalent. I also have given information on molecular geometry, how you identify the shapes of the molecules, your intermolecular forces. So for those that actually do want the notes, can you just make sure that you do let David Ball know, because he will then tell me, so I can then actually send on the notes to him. And then that means that you'll have kind of a step-by-step for chemical bonding as well. Okay. Yeah, I think that's all the questions. Okay, look, we're going to leave it there at that. I really appreciate all of you joining. Thanks for all the questions. Really, really good questions. Hopefully some of it helped. You know, like I wish we had more time because we could go through a lot more, but obviously, you know, we only have an hour and a half, so we can only go through a set amount. So hopefully that will be enough to get you through your exams. Okay. Let me go Jasmine there now. Okay. Right, we're going to end that meeting now. So thanks a million for everyone that's joined. And again, if you want the notes, just make sure you reach out to David Ball and he'll send them on to you. Thanks a million.